So in our previous experiments, what we have done was to use a reductant to quantitatively reduce the copper-2 into copper-1 before we carry out the reaction. But in this case, we're actually detecting the reductant. So because proteins can quantitatively reduce copper-2 from copper-1, so this is believed to be to have something to do with the peptide bond. We have looked into the literature, and no single paper has given us the definitive answer as to the mechanism of this reaction, but people apparently believe this works. So basically, because we have this copper-based assay based on gold nanoparticles, we could actually use the protein as a reduction agent, as a reductant, to actually quantitatively determine the amount of reductant in the solution using this strategy. So basically, again, we use the presence or the creation of the copper-1 as an indirect assay for the presence of proteins in this case. So as you see in here, if we add in the gold nanoparticles in the proteins and a reductant plus the copper-2, only the ones where we have the presence of copper-1 has a change in color. The other solutions don't have changing colors. So this assay actually allows us fairly high sensitivity and a broad detection range. Currently, our assay is about 2 orders of magnitude higher in the dynamic range than the BCA or Bradford assays that are typically used to estimate the quantity of proteins using the color of a certain assay. So we hope that these types of methods will be useful for on-site point-of-care sort of assay for quantifying proteins in many types of scenarios. So the next example for the gold nanoparticle-based detection is one of the things that I originally wrote in the abstract that I want to tell you about. So this mechanism is also based on the aggregation of gold nanoparticles, but the mechanism is somewhat different. So what I've told you so far are all based on chemical ligands that pull the gold nanoparticles together as a result of chemical reaction or presence of certain molecules in the solution that we assay. In this case, it's slightly different. This is based on replacement. So we initially modified the gold nanoparticle with the rhodamine molecule on the surface. So the rhodamine initially, of course, is fluorescent. Once it absorbs on the surface of the gold, its fluorescence is quenched. At this stage, it also acts as a dispersant that allows the gold nanoparticles to be fairly well dispersed in aqueous solutions. But if we have ligands like this in the solution, what happens is that because the thiol would bind to the surface of gold more strongly than the rhodamine. So the rhodamine is believed to bind to the surface of gold via electrostatic or van der Waals interactions. Because the sulfur-gold bond is much stronger than that, so it's believed to replace the rhodamine from the surface of the gold. So 2 things will happen after this replacement. One is the quenched fluorescence of the rhodamine will be released. Thus, we will see fluorescence in the solution if we are looking at fluorescence. The second thing is because initially the highly charged rhodamine allows the gold to be completely dispersed in the aqueous solutions. But after we do this, the gold nanoparticles will start to aggregate. So the second event you will see is that the color of the solution under white light will actually change from pink to blue. So we actually use this reaction to assay for a very important enzyme, acetylcholinesterase. So acetylcholinesterase could very selectively catalyze acetylcholine into this molecule, and the presence and the amount of acetylcholine in the in the cerebral spinal fluids of humans and also mice is believed to be connected to Alzheimer's disease. Somebody mentioned Alzheimer's disease just now. This is actually becoming a very difficult disease to diagnose before before its onset, and because the expected lives of humans, particularly in developed nations, is increasing rapidly to over 80 years old. Some epidemiologists think that in about 40 to 50 years' time, over half of the people over 80 years old will actually have Alzheimer's disease or symptoms like it. So the development of an in vitro method to pre-evaluate the high risk for Alzheimer's disease is very important. And some clinicians believe that the presence of the amount of acetylcholinesterase, particularly in the cerebral spinal fluid, is related to Alzheimer's disease. This is one of the motivations for doing this reaction. So as I showed you, as I explained to you just now, if we have this rhodamine labeled gold nanoparticles and adding the enzyme and the substrate, what you'll see is that the color, the absorbance will change. At the same time, the fluorescence will also change. This sort of acts as a dual readout for the presence of the acetylcholinesterase in the diagnosis of Alzheimer's disease. So something else that we thought that this detection for acetylcholinesterase is useful is the detection of pesticide residues in vegetables and fruits. That's because certain pesticides could make the acetylcholinesterase completely inactive. And then, of course, because we have an assay for cholinesterase, whatever makes it inactive will also be easily detected in this example. Without going into the details, I'll just say that this is an assay that allows us to, again, quickly look at basically toxins for acetylcholinesterase, and many of them are pesticides. So this concludes the scientific part of my talk. And before I close, I'd like to advertise a little bit about the journal Nanoscale, which is a joint venture between Royal Society of Publishing and our center. So the journal started in 2009, actually at the end of 2009. So this year is the first year when we had a full impact factor. That is, we have 2 full years of publication. The impact factor is 5.9. So people working in Nanoscale are more than welcome to submit to Nanoscale. So the website is here. With that, I would like to thank my collaborators and the funding agencies, and thank you.